Imagine a telescope so powerful it can peer back in time to the very birth of galaxies. The James Webb Space Telescope isn't orbiting Earth. It's stationed 1.5 million kilometers away at the second Lagrange point, a cosmic sweet spot where gravity and sunlight balance perfectly. There, shielded from the sun by its massive golden mirrors and 5-layer sunshield, Webb unfolds the universe's oldest secrets one photon at a time. Imagine a giant eye 6.5 meters across, composed of 18 hexagonal segments, each polished to extreme precision and aligned to within mere nanometers. That's the heart of James Webb's ability to see the early universe. The story begins with the mirror materials selection. NASA documented that a formal evaluation process chose beryllium for the primary mirror segments because of its performance in cryogenic conditions. It holds shape, has low coefficient of thermal expansion, and is light yet stiff. From the Advanced Mirror System Demonstrator program, government and contractor teams developed sub-scale beryllium mirrors to prove the concept. Each of 18 segments had to go through a long manufacturing path, from ultra-light beryllium blank, machining, polishing, cryogenic testing, coating with gold for infrared reflectivity, and integration into an actuation assembly capable of 6 degrees of freedom. Once in orbit, the segments must behave as if they are a single continuous mirror. That means wavefront sensing and control motors and actuators adjust each segment in piston, tip, tilt, and curvature until the total mirror forms the perfect surface. In short, a scientific masterpiece built from 18 precision pieces, engineered to survive launch, unfold, and aligned in the cold of space. Picture a tennis court-sized kite unfurling in space. The barrier between the blistering sun and a telescope so cold it can see invisible infrared whispers of distant galaxies. That is James Webb's sunshield, 5 ultra-thin membranes of Kapton coated in aluminum and silicon, stacked like pancakes and tensioned in orbit. One side faces the sun, Earth and the Moon reaching temperatures around 85 degrees, while the protected cold side, where the optics and instruments reside, is held at about minus 233 degrees. That huge thermal difference is only possible because of the multi-layer shield. Its deployment was a feat in itself. The 5 layers had to be stowed, then unfurled, separated, tensioned, and precisely aligned thousands of kilometers from Earth. The critical design review for the shielding confirmed that the design satisfies the thermal deployment and stray light requirement. And it's very important for James Webb infrared instruments since it has to detect the faint heat signatures across the universe. The telescope itself must be extremely cold, otherwise its own heat would mask the signals. The sunshield enables near-passive cooling of the observatory structure. Rather than orbit Earth directly, James Webb travels to and operates from a unique vantage, the second Sun-Earth Lagrange Point, L2, roughly 1.5 million kilometers from Earth, on the side opposite to the Sun. At L2, the gravitational forces of the Sun and Earth and the orbital motion of the spacecraft balances in a way that allows James Webb to stay in a stable configuration within minimal fuel use, continuous communication with Earth, and consistent solar orientation, which is very helpful for keeping the sunshield properly aligned. This orbit gives James Webb a cold, stable environment ideal for its infrared mission. Behind the mirror and shield lies the heart of James Webb science capability. Its suits of infrared instruments designed to peer through cosmic dust, see the first galaxies, and analyze distant exoplanets. These include NIRCam, near-infrared camera for high-resolution imaging in the near-infrared, NIRSpec, near-infrared spectrograph, which can observe up to 100 objects simultaneously using a microshutter array, MIRI, mid-infrared instrument, which operates in the mid-infrared, needing very low temperature, 7 Kelvin, for its detectors, and FGS, fine guidance sensor, for pointing stability and additional science. NASA describes that Webb's innovation includes ultra-sensitive near and mid-infrared detectors and microshutter arrays. These instruments demand extreme precision, low noise, and cryogenic operation. They push the boundaries of detector technology, including the readout electronics, operating at very low temperatures. Although much of James Webb cooling is passive, one instrument demands something more. MIRI's detectors needs to be at 7 Kelvin, which is minus 266 degrees. Passive cooling alone could not reach those temperatures, so the mission incorporates a dedicated cryo cooler. The system uses helium gas, a pre-cooler, high-efficiency pump, and a thermal link to the instrument. Moreover, the telescope backplane and structure were engineered to maintain optical alignment at 40 Kelvin, which required a new approaches to cryogenic stable structures. James Webb uses a layered thermal architecture, sunshield for bulk cooling, passive radiators for an instrument, and an active cryocooler for the coldest detector. From launch configuration to fully operational in space, James Webb deployment sequence is like watching complex origami in zero gravity. The sunshield unfolds, the mirror wings open, the mirror segments rotates and latch, and the actuators begin aligning each segment. NASA calls these folding, lightweight, adjustable cryogenic mirrors among its innovations. Once the optics are open, wavefront sensing and control kicks in. The system takes slightly defocused image, analyzes the wavefront error, then sends commands to actuators to adjust piston, tip, tilt, and curvature until the image forms as one monolithic mirror. Reference models such as optical simulation testbed were used to train and validate these algorithms and hardware. In other words, James Webb doesn't just work once deployed. It becomes a single, finely tuned observatory in space. Behind the telescope and shielded lies the spacecraft bus, the housekeeping system of power, communication, attitude control, and thermal regulation. James Webb uses the Deep Space Network to transmit data back to Earth, manages its orientation to target objects, and ensures structural stability. The backplane supporting the mirror weighted 2.5 tons and maintained nanometer level stability in cryogenic conditions. The architecture called for a semi-rigid backplane to allow ground verification yet maintain stability in space. In short, while the mirror and instrument grab the spotlight, the bus and control system are what keep James Webb alive, pointing where it must, relying data home, and surviving the harshness of space. Behind every beautiful distant galaxy image of James Webb is an act of human ingenuity, from mining beryllium to folding a tennis court-sized shield. to aligning 18 meters in the cold of space, to reading the faintest infrared photons from billions of light years away. Don't miss out. New videos drop every Sunday evening. Hit subscribe and ring the bell so you are the first to watch.